Hello students, now today as we see in previous lecture we are studying about the application of Heaviside expansion formula. Today we will see some more examples to solve or to apply Heaviside expansion formula to these examples. Now take one example such as using Heaviside expansion formula, using Heaviside expansion formula, using Heaviside expansion formula. Solve or find inverse Laplace transform of s square minus 6 s cube 4 s square plus 3s. Now, first of all, we have to check first condition. Degree of numerator must be less than degree of denominator. So degree of numerator is 2 here and degree of denominator is 3 here. So we can apply Heaviside expansion formula to this example. Since we know that Heaviside expansion formula as inverse Laplace transform of f upon g is summation I is equals to 1 to n f of alpha I upon g dash of alpha I e into e raised to alpha I. Correct? Where alpha it is, where alpha I are zeros of g. Now we have to calculate inverse Laplace transform of s square minus 6 upon s cube plus 4s square plus 3s, and here we have to solve this example by using Heaviside expansion formula. If this statement with this example is not given, then we can apply partial fraction also to solve this example. But whenever a clear statement is given using Heaviside expansion formula, you have to use only this formula to solve this example. Now, in this formula, we need g dash of function g, means derivative of g, and we have to calculate alpha I, means zeros of g. So first of all, let f of s is equals to s square minus 6 and g of s is equals to s cube plus 4s square plus 3s. Now to find zeros of gs, to find zeros of gs, put g of s is equals to 0. So we will get s cube plus 4s square plus 3 is equals to 0. Correct? 3s, sorry. 3s. 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 Yes. To find the zeros of Gs, we have to put G of S is equals to 0 and S cube plus 4s square plus 3s is equals to 0. Since we have s in multiplication of each term, so we can take s common outside. We will get s square plus 4s plus 3. And this is quadratic equation. We can solve by using method to solve quadratic equation as follows: s square plus 3s plus s plus 3 is equals to 0. This implies that s taking common s outside, we will get s plus 3 plus 1, we will get s plus 3. Now s plus 3 is common, so taking outside s plus 3, here we will get s and plus 1, so we get s plus 1. And this implies that zeros of Gs are 0, minus 3 and minus 1. There are 3 zeros of Gs which are 0, minus 3 and minus 1. Now, since in function summation I is equals to 1 to n f of alpha I upon g dash of alpha I, means it shows that we have to calculate first differentiation of g of s. Since g of s is equals to s cube plus 4s square plus 3s, hence g dash of s is equals to 3s square plus 8s plus 3. It is our g dash of s, which is 3s square plus 8s plus 3. Now we have to calculate g dash of alpha I, where alpha I are zeros of g. So alpha 1 becomes 0, alpha 2 becomes minus 3 and alpha 3 becomes minus 1. So g dash of 0, we will get 3 only. It becomes 0, 0, 0 plus 0 plus 3. Then g dash of minus 3, we will get 3 into minus 3 into minus 3 square, that is 9, plus 8 into minus 3 plus 3, and we will get 9 is 27 minus 24 plus 3, and we will get 6. Correct? Now g dash of minus 1, we will get 3 into 1 plus 4, 8 into minus 1 and plus 3. So we will get 3 minus 8 plus 3, which will give us minus 2. So we have g dash of 0 is equals to 3, g dash of minus 3 is equals to 6, and g dash of minus 1 is minus 2. Now, in formula we need f of alpha I and alpha I are 0, minus 1 and minus 2. Since in this formula we want f of alpha I, which is in numerator, so f of s is given as s square minus 6. S square minus 6. We have to find f of 0, which will give us minus 6. F of minus 3, which will give us minus 3 square. Minus 6 means 9 minus 6, that is 3. And f of minus is 5. Now we have all the values which were asked in right hand side. So we write inverse Laplace transform of s square minus 6 upon s cube plus 4s square plus 3s is equals to f of alpha I g dash of f of alpha 1 g dash of alpha 1 e raised to alpha 1 t, f of alpha 2 g dash of alpha 2 e raised to alpha 2 t, and f of alpha 3 g dash of alpha 3 e raised to alpha 3t. Now we know that alpha 1, alpha 2, alpha 3 are zeros of g. We have to put values of alpha 1, f of alpha 1, g dash of alpha 1, f of alpha 2, g dash of alpha 2, and f of alpha 3, g dash of alpha 3 in this expression. F of alpha 1, that is minus 6. G dash of alpha 1, that is 3. E raised to, and value of alpha 1 is 0 into t, plus f of alpha 2, and alpha 2 is minus 3, so we can write it as 3 upon g dash of alpha 2, which is 6, e raised to alpha 2 means minus 3t, plus f of alpha 3, that is 5, g dash of alpha 3, that is minus 2, and e raised to minus 1. So it is 3 to the 6 minus 2, 3 to the 6, 1 upon 2 e raised to minus 3d, and minus 5 by 2 e raised to minus t. Correct? It is the required result for our example. Remember, we have to first of all find zeros of g of s, find zeros of g of s, and whatever zeros of g of s are there, we have to put with the name of alpha 1, alpha 2, alpha 3 up to alpha n, and by using these zeros or roots of that equation, we can find f of alpha 1, f of alpha 2, f of alpha n. Similarly, we have to find g dash of alpha, and by putting values of alpha 1, alpha 2, alpha 3, we have to find the value of g dash of alpha by respectively zeros of that g of s, and by putting in these values in the formula of Heaviside expansion formula, we can easily deduce the result for particular example. Now take one more example, which is as follows. Find the inverse Laplace transform of 3s plus 1 upon s minus 1 upon s square plus 1. Correct? Yes. We have to calculate or find the value of this function. Since we know that, we have to consider first that f of s is equals to 3s plus 1, g of s is equals to s minus 1, s square plus 1, which is equals to s cube plus s minus s square minus 1, and we can write it as s cube plus minus s square plus s minus 1, it is g of s, and similarly g dash of s becomes 3s square minus 2s plus 1. Now to find zeros of g of s, put g of s is equals to 0, so we will get s minus 1 s square plus 1 is equals to 0, s minus 1, and it will give us s minus I, s plus I. Correct? So we have zeros of gs as zeros of gs are 1 plus I and minus I, where I is an imaginary number. Now, by using these zeros, we have to calculate each term of the formula and try to get exact result for this particular example. Now, since f of x is equals to 3s plus 1, therefore f of alpha 1, that is f of 1, zeros of g of s will give us 3 into 1 plus 1 will give us 4. F of alpha 2 means f of I, which will give us 3 into I plus 1, and f of alpha 3, which will give us f of minus I, and it will be minus 3i plus 1. Correct? Now, g dash of s will be 3s square minus 2s plus 1 yes. Now g dash of alpha 1, that is g dash of 1 only, we will get 3 1 square minus 2 into 1 plus 1. 3 minus 2 becomes 1 plus 1, that is 2. Now g dash of alpha 2, that is g dash of I, we will get 3i square minus 2i plus 1. 3i square means minus 3 minus 2i plus 1, which will give us minus 2 minus 2i. And g dash of alpha 3, that is g dash of minus I, 3 into minus I square minus 2 minus I plus 1. Again minus I square becomes minus 1. So minus 3 minus 1 has become plus 2I plus 1. So we will get minus 2 plus 2I for g dash of alpha 3. Now putting this value in our formula, inverse Laplace transform of 3s plus 1 upon s minus 1 s square plus 1 is equals to f of alpha 1 g dash of alpha 1 e raised to alpha 1 t, f of alpha 2 g dash of alpha 2 e raised to alpha 2t, and f of alpha 3 g dash of alpha 3 e raised to alpha 3t. Now putting value of f of alpha 1. f of alpha 1 is equal to 4 4 as it is. G dash of alpha 1, that is 2 e raised to, value of alpha 1 is 1. So 1 t is t, e raised to t only. Now f of alpha 2 is 3i plus 1. G dash of alpha 2 will give us minus 2 minus 2i e raised to it plus f of alpha 3, that is minus 3i plus 1 upon g dash of alpha 2, that is minus 2 minus 2i, minus 2 plus 2i, and e raised to minus it. Correct? We will get 2 e raised to t, taking minus outside, we will get minus 3i plus 1, 2i plus 2 e raised to it, minus minus will cancel, we will get 3i minus 1 and 2 minus 2i e raised to minus it. It is the required method for our this expression. In this example, if we go through by partial fraction, we will get result same as we have by using Heaviside expansion formula, but it takes number of steps to solve that example by using partial fraction. It is easiest method, and you have to do very basics of our knowledge to find roots of particular example, and we have to find values of function at that roots and put these value into formula. We will get easily the result which we need. In next lecture, we will see some more examples which are depends on Heaviside expansion formula. It is easy and very understandable method to solve such type of example. So please try to do practice of this method. It is very important as exam point of view. We will see some more example. Till then, thank you. Bye.